Fantastic. Fantastic. Okay. Okay. Well, good afternoon, everybody. It is with great pleasure that I introduce today's speaker, Víctor Enguita. Víctor is a PhD student in Madrid and has been working with friends of Dias, Belén Gavella, who's visited us as well, physically and virtually. Víctor has actually applied for a postdoc scholar position here. So this will be an opportunity for him to introduce his research to Dias. And he's going to tell us about a combination of a bunch of papers that he has written, which is quite impressive for a PhD student. So I give you the floor, Víctor, please.
Yes. Okay. So first of all, I like to thank you for inviting me for this talk. It's a very nice opportunity. And what I will do today, I will give an extended version of the talk that I gave last week in the workshop for future accelerators, where first I will introduce some of the fundamental aspects of an alternative approach to some of the theoretical problems involving the Higgs. And then I will present some of my recent results put forward in collaboration with my thesis supervisor, Belén Gavella, and our MIT collaborator, Thomas Steingasser, which together with the results of other collaborators suggest that beyond the standard model scenarios, successfully realizing solutions for these problems under this particular interpretation could very generically produce telltale experimental signals at future colliders. So they could become, these scenarios could become relevant in the next years as not only these colliders, but actually new experiments with better sensitivities are commissioned. Now, let me start already. Okay, sorry about that. I don't know. I think I'm not in the right mode for this.
Yeah, I think sometimes if you probably have to go to full screen on your, yeah.
It's not this full screen. Yes, that's it. Okay, sorry. Yeah, that's okay. It.
Yeah.
Okay. So let me start my talk by commenting on the very familiar potential for the Higgs, which, as many of us will know, suffers from severe problems of fine-tuning. Perhaps most relevant is the problem of tuning on the mass of the Higgs, which is known to receive radiative corrections, which are quadratic with any scale of new physics beyond the standard model, with that very plausibly also including gravity. So it is expected to be of that very high size. For instance, it is expected to be of a very large size. If gravity is included, then of course of the size of the Planck scale. Now, in contrast, what the value that we have found experimentally for this mass is very tiny. It's only 125 GeVs, which tell us that extreme cancellations must have happened among the different very large contributions to this mass, so that in the end, this very small value is produced. Now, this, of course, calls for a theoretical explanation, and our lack of one is what we call the Electroweak or Higgs hierarchy problem. The usual approach to the Higgs hierarchy problem is that of technical naturalness, as it was formulated by 't Hooft originally, and it consists on postulating the existence of a new approximate symmetry of nature, which becomes exact when the mass of the Higgs is taken to 0. Then the mass is said to be protected by the symmetry, and when it is restored, the symmetry will make sure that the necessary partial cancellations happen to the required degree of accuracy, so that in the end, a very small mass is generated from the in principle large first contributions. However, even though this has been by far the most successful approach to the problem in the last decades, and even though it has brought into the field a lot of interesting new models and insights, The fact is that it has also not been able to fully account for the tuning found in the mass of the Higgs, and therefore it becomes pertinent to understand whether there could be other alternative approaches to this problem which could eventually shed more light on it. Now, the alternative approach, which I endorsed in this paper and we endorsed in our previous publications, becomes apparent once one takes one step back and looks at the other mysteries which surround the potential for the Higgs. For instance, one can look first at this independent term of the potential, the constant V0, which can be linked, is linked to the standard model's prediction for the energy density of the vacuum, which, as is also very famously known, is catastrophically larger by many, many orders of magnitude than the measured value in the form of the cosmological constant. This is the cosmological constant problem. Now, I have to say that this is a much less well understood problem than the Higgs hierarchy problem. And well, it can be treated as a fine-tuning, but this will be an important, we will take another interpretation for this. Now, another interesting property of the Higgs potential becomes apparent once one considers the running of its quantic coupling lambda. This coupling here, and well, as it was found very soon after the discovery of the Higgs by Butazzo and collaborators in this very relevant paper, the mass of the top, which provides the dominant contribution to the running of lambda, you can see it here, Ritsukawa, is just such the quantic coupling of the Higgs becomes negative at a very large running scale. In the case of the standard model, if the standard model is the only physics found until this point, this will be about 10 to the 11 GeVs. And we call this scale the instability scale, which will be brought, we will bring up later. Now, the quartic of the Higgs becoming negative tell us that at this very large instability scale, there should be a turn in this potential, which should generate a minimum at an ultraviolet scale, larger than this instability scale. And what this tells us is that the Electroweak vacuum of the Higgs potential is actually not a true minimum, but rather a false vacuum from which the Higgs field can tunnel until this into this other minimum found at large energies. Now, this surprising matter, which has sparked a lot of questions in the community and has been the subject of many papers in the literature. Like it's something that needs an explanation, is why does nature seem to have chosen values for the both parameters, that is the Yukawa of the top and the lambda, which are just in this very narrow area of the parameter space where the Electroweak vacuum turns to be metastable. That is where its typical its lifetime, its typical decay time will be smaller than the current age of the universe, actually by quite a bit. Explaining this is also another open problem, which is relevant for the community. Now, the key observation, which is actually backing some of the claims that we make in this paper, is that all of these three parameters have something in common, which is that they all seem to have near critical values, right? So for instance, the energy density of the vacuum seems to be very small, it's close to zero, which can be interpreted as it being very close to the point of transition between the de and anti-de Sitter phase of space-time. In the same way, the very small value of the mass of the Higgs in comparison to the Planck scale tell us that it is very close to zero. that it's being very close to zero. Well, it can be taken as the mass being extremely close to the transition between a spontaneously broken electroweak vacuum and an unbroken phase. And finally, in the case of the quatic, together with the mass of the top, we seem to be on the verge of coming into the stable phase, but not quite, right? So we are extremely close to the point of transition to this stable phase, even though we are in the unstable one. This takes us to formulating the near-criticality, an alternative interpretation of Higgs physics, which hypothesizes that this is no coincidence, and actually there was some unknown underlying dynamical mechanism, presumably happening in the early universe, which selected these parameters to be near-critical. And in that sense, the surprising values of these parameters that we observe in nature would not be but a consequence of such a mechanism. And well, of course, this introduces other open questions, right? The first of which, the most obvious which, is, well, which could those dynamics be? And well, the motivation for this is also that it seems that there is many dynamical systems where the criticality of the dynamical parameters is a feature of the dynamical variables. And I will mention here there is several proposals in the literature for this kind of mechanism, of which I would actually mention two. The first of these relies on an emergent property of some dynamical systems, which is called self-organized criticality, and is actually present in some contexts matter physics systems, but also in systems like sand or snow, many body systems with many degrees of freedom, where, well, it actually is in charge of explaining why avalanches work and this kind of thing. Now, the property of these systems with self-organized criticality, the main property is that in these systems, the critical values of the dynamical variables will act as attractors. So at the end of evolution, what one finds is that the values of these dynamical variables will typically be very close to the critical values. This, in the context of particle physics and cosmology, was proposed firstly by Giudis, McCullough, and Yu in this paper, Self-Organized Localization, and they are actually able to reproduce the right conditions for self-criticality to emerge by considering the parameters of the Higgs potential as dynamical variables in the context of inflation and on the background of quantum fluctuations. So these quantum fluctuations will create some dynamics that are governed by some stochastic equations, and this will recreate the right conditions for that. Now, I will also mention this other idea, which was brought forward by Justin Curie and Onkar Parrikar, which takes inspiration in string theory and the concept of eternal inflation. And in this realization, what one has is a landscape with many vacua, in which, well, the dynamical fields can jump from one vacuum to another, tunneling between them, right? And what they observe in this scenario is that some observer which explores the network will much more efficiently explore the regions in which the vacua seem to have lifetimes which are comparable to this page time, which are not far away. This is also metastable configurations which are not far away from the situation that we find in the standard model. And actually, in this case, there is a loose argument that also allows to explain the mass of the Higgs, because the small mass of the Higgs, because having a metastable electroweak vacuum with the right with the right decay time will usually map, get you into parameters at the Electroweak scale for the Higgs field. Okay, now what we will do for the remainder of the paper, for the remainder of the talk, we will not talk anymore about specific mechanisms realizing this this near-criticality of the parameters, and we will just assume that there was indeed a mechanism setting the Higgs parameters to be near-critical. And what we will do is to look at the consequences for lower energy physics, for things that we can measure, of these when these scenarios realize viable solutions for, in particular, the Higgs hierarchy problem. Now, another very important concept which I need to introduce is just that under the assumption of metastability, which seems to be backed by observation, the mass of the Higgs is actually bounded from above. So the bound looks like this, where mu I is just the instability scale, where the lambda becomes 0, which I defined it earlier. And this is just the beta function of lambda at that scale. Now,
sorry, may I jump? So when you say it is bounded from above, you mean that if the Higgs mass was heavier than this, then we would definitely be in a metastable vacuum and we would tunnel to another vacuum?
I will go for that in a minute. So it's actually, if it was larger than this, then we would, the universe would look quite differently. So there wouldn't be electroweak vacuum, basically. So it's like, in order for both the ultraviolet vacuum and the ultraviolet and the electroweak one to exist, there should be, this bound should be fulfilled. Okay, yes, and this is actually because what I was going to say right now, which is that the bound comes from looking at the conditions for the maximum separating, making the barrier between the two different minima. So, so maybe I can
the
go.
word that worried me in there was meta, because stability, I understand that would give you a bound, but I guess metastable is when the two vacua are exactly at the same depth. So yeah, anything, I guess that would give you a bound that if you go above or below that, then the other vacuum becomes deeper. Yeah. Good, thank you.
Okay. Yes, I mean, I'm using the word metastable maybe in a different, a little different sense, just meaning that it's stable enough. I think this might be the case in this context. So I call the minimum metastable because, well, the tunneling, it's not a situation where the tunneling will happen very certainly, right? We can see that later maybe. So anyway, like, yes, so I mean, yes. So the stationary, in this context, when I say metastable, what I mean is more like, this is the condition for the Higgs, for the electroweak vacuum to be a false vacuum, but also a vacuum, right? So there is a true vacuum there and not just, otherwise what would you get is a saddle point actually from which you can roll classically to, yes. So,
what is the intuitive understanding of mu I? You've said that lambda effective of mu I equals 0. That doesn't look like any natural point in the effective potential.
Well, so this is just when you, yes, so I mean, mu I is just defined as the point where this crosses 0, which makes, I mean, you will see how this very naturally enters.
But I mean, when you're talking about mu of lambda effective, there are always higher point. There's a 6-point vertex, there's an 8-point vertex. So it doesn't mean that it's unstable there.
Well, I mean, this is where you know that around that point, the potential will change, right? And you will start to develop the next minimum. So this is where the barrier develops between the two.
Yeah, I think that is how it's defined. But yeah, by effective, I don't know how many loops has been taken into account, but if I remember
yes.
from this paper, it was probably up to 2 loops, right?
But,
I think we're actually doing,
any looping expansion, if you go beyond 1 loop, you're going to find that the 6-point vertex is non-zero and probably positive. So that's going to give you a stability there, even though lambda 4 is negative. The gamma 4
yes.
4-point vertex is negative.
Yes, so now I get you. I mean, usually this is what you will. So at some point, if there is some order 6 operator or something in the potential, it will become dominant and generate an extra vacuum at the end of, like at higher energies, right? After this turning point. I don't know if you are, what you say is in relation.
I think what Denjo is asking is that up to which point, like when you say lambda effective equal to 0, do you mean you've taken into account the 4-point function or the 6-point function or the 8-point function? But I guess that is, in the definition,
yes.
it is defined as that, yeah.
Yes, so I believe this is, we actually consider the evolution at up to 3 loops.
Oh, wow.
But this is for the case of the standard model, right? Where you know very well what happened.
Yeah.
And for other beyond the standard model scenarios, it was a 1 loop or 2 loop calculations.
Yeah, I mean, this is completely assuming that nothing else is there up to the Planck scale. It's just the standard model.
Yes, this is plain standard model, and you assume that
Lambda
this is
effective would be defined as the 4th derivative at 0 of the effective potential.
I guess so.
To some constant.
Yes, that's correct.
Yeah. Go ahead.
Yes, okay. So maybe I will quickly tell you this. So yes, as I was saying, the way of deriving this bound, so you can depart from the stationary equations of motion for the Higgs potential and look for the conditions for this maximum at the barrier between generating the barrier between the electroweak potential, the electroweak vacuum, and the ultraviolet one will exist. And for that, you can expand the equation around the instability scale, because this should happen exactly around that scale, where lambda effective is proportional to its beta function. And you get, after some manipulations, this equation here, which it can be shown that the 2 sides can only take equal values if if the mass is below some critical value, which gives the bound. Oh my God. Yes, okay. And graphically, this just looks like this. So you can see that when the mass is below some critical value, there is the barrier, and it disappears when the mass is too big. So in this case, since we would be able, this is not a minimum, and we would tunnel classically, we would roll classically to this ultraviolet maximum. This is not in agreement with observation, and therefore we should be in the other phase. Now, I mean, one can see how, if one wants to prove that, if one wants to explain why the mass of the Higgs is so tiny, it could be extremely useful to have a bound, an upper bound on it like this. And this is indeed the case, but just not quite in the standard model, because as I said, the instability scale is so large, the middle value is 10 to the 11 GeVs, leading, sorry. Okay, leading to a very weak bound, which is not enough to account for the Higgs hierarchy problem. And our point in our paper was that, in many, actually it's very generic of many beyond the standard model extensions, that we will find regions of the parameter space where this is a bound is strengthened considerably. And in fact, this is so true. Normally this is very true, and it's often easy to find regions of this parameter space where the mass of the Higgs, the amount of the mass of the Higgs is of the order of the tera electron volt, which is very nice and would fully account for the Higgs hierarchy problem. Now, the most obvious way to lower this instability bound is to add fermions to the standard model, because in the same way as the top provokes the decrease of the quartic of the Higgs, generically these fermions will also introduce negative contributions to the beta function of lambda and will accelerate its running towards zero. So for instance, we consider the case of the right-handed neutrinos, where the contributions for the beta function at one loop looks like this. And for large enough Yucabas, which are still of feasible values, you can see here some examples, we see that the instability scale actually becomes very small, and it even approaches the mass scale associated with these neutrinos. Now, however, anyone who has worked with this kind of calculations might be lifting an eyebrow now, because of course, getting such a, the fermions are essentially too good at their job and will typically destabilize the electroweak vacuum too much, and by making the instability scale so small, and produce shorter lifetimes for the electroweak vacuum, which will be shorter than the age of the universe. The solution is very easy then. One has to be careful and add scalars to this. Consider theories which contain scalar degrees of freedom, which will typically tend to stabilize the vacuum, the electroweak vacuum, in a way that we will see in a few slides. So you can see here the effect. What's the effect of these scalar degrees of freedom, where after this threshold here, when the scalar fields kick in, they will typically, you can see it not very well maybe in this plot, but you can see it in the red line, the evolution of the line will be softened. So you won't obtain such a sharp decrease in the value of lambda in this case.
Sorry,
Now,
may I jump in? I mean, as you said, yeah, anybody who's worked on this, including myself, you usually add stuff to stabilize the potential. But I'd never seen anybody actually then add stuff to destabilize it, to actually put an upper bound on the value of the Higgs mass. And then I guess you could rule out some models using this, right?
I could what? Sorry, I didn't
you
catch.
could rule out some models, right? For example, if you say, I don't know, if you had 10 right-handed neutrinos or something, then
yes.
Yeah, that's a very clever thing to do. I'd never thought about it.
Nice. I mean, this is actually, yes, it's something we discussed, but we never did. And yes, like often in many, probably if you check this in many models that are out there, you would find this kind of problems, right? And normally people doesn't account. And of course, I mean, you need like an upper layer of scalar fields or something to actually stabilize this afterwards.
Yeah, very good.
Yes, I mean, in fact, it's been fun, right? Because all the literature tries to make a larger instability scale to stabilize and the opposite. Yes. Okay. Yes, so I was now just going to list very quickly the references in literature where this kind of thing had already been considered, where, well, in these papers here, it was vector-like fermions, which were used to lower the instability scale. And in this one, they consider heavy neutral leptons. But in these models, it was always effective field theories, which didn't let them play properly with the phenomenology of these theories. And recently, two papers which consider ultraviolet complete models have appeared. The first of which is this by our collaborators Maximilian Detering and Tebong Yu, in which they consider an axion-like particle. And now we, well, this March, we put forward some months later this paper in which we consider the specific case of the Majoron completion for the Type-I Seesaw mechanism. And I will focus now for a bit on our model, which, well, as I said, this paper was put forward with Belen and Thomas, my supervisor and our collaborator. And we chose it because it is a well-motivated model, which also has the right components to realize this scenario. So we have the motivations are that it realizes a Type-I seesaw mechanism for the Higgs, and also that for the Higgs for generating the masses of left-handed neutrinos, and also that certain realizations on which we will focus also allow for large masses and for smaller, like large couplings with the standard model, and smaller than usual masses for the neutrinos. This is actually something that is a bit detached. I mean, you can also realize this in other models, not only in the Majoron, but this is the motivation for the low scale family within the Majoron model. Now, the fermion, the particle content in the model is the following. It will contain fermions, right-handed neutrinos, which couple to the standard model through this Yukawa coupling, where this is the lepton doublet and this is the Higgs. And it will have a typically large Majorana mass with which will realize a seesaw mechanism to produce light masses for the neutrinos. And the particularity of the Majoron model is that the Majorana mass is generated by the coupling of the neutrinos with some heavy scalar field, which when it takes a BEV, will generate a mass like this for them. Now, in this model, we actually can already foresee like the hierarchy that we will require for the masses of these particles. So typically, you have a scalar that is heavier than the fermion, and you want it to appear after the instability scale. This is the hierarchy that we assumed. Actually, you can try to invert it, so you can try to put the instability scale after the scalar, but this typically will not work, since the bounds that you get, the metastability bound, will still be too large to fully account for the tuning problem. So you won't get a quality solution for it, only a partial one. Okay, and we are working in the symmetry-protected seesaw scenario, which is a very popular one in the literature and something that is often assumed, because it allows to lower the values of the masses of the neutrinos. So,
sorry, I've got questions. Can you go back a little bit? I want to see which Yukawa term showed up in the stability bound. Was it Y nu? Oh, it is Y nu.
Yeah.
Okay.
It's coupling with the Higgs that will generate the change. Yes.
And is the mass of your neutrino then, it is not independent of the Yukawa, right? Yes, I can see.
Well, it depends on this Yukawa. So
But it also has a Y nu in it.
It doesn't have a Y nu in it.
So what is that M nu you've got on the right side?
Sorry again.
So on the right-hand side, the top equation.
Yes, so MN.
And then there's
you mean this?
He has integrated out. He has integrated out the right-handed fermions. I believe is what he's done.
This is yes, that's it. So this is what you do to obtain the masses for the left-handed neutrinos, right? But actually, I was just going to say how well our calculation in the symmetry protected seesaw scenario detaches from this calculation, because the extra symmetry that you endow with that you provide to the extra neutrinos, to the right-handed neutrinos, you basically endow them with lepton number symmetry. Provokes that when the symmetry is exact, this combination here vanishes, and the left-handed neutrinos will have masses which are proportional only to the breaking of the masses. So we kind of we neglect this part for the rest of the analysis, which and actually our analysis depends only on this combination, which is the trace of y dagger times y.
What was W into be? Your little W in the mass matrix?
That's the wave of the singlet.
The wave of the singlet, yes.
Was the wave of the singlet, okay.
Yes, which we assume typically to be large, so this. Yes, also, yes, this realizes a hierarchy. I mean, well, I will explain that later. So maybe I can go. I don't know if I finish with this. Yes, so actually we also introduce this assumption for the texture of the Yukawa, coupling the right-handed neutrinos to the standard model, which, well, this is one of the few textures, there are 4 in total, which are allowed by the symmetry-protected seesaw scenario. And it has the nice property that the trace of these 4 powers of the Yukawa is proportional. It's just the square of the trace of 2 of them. So this will introduce, this is a simplifying assumption that will make the analysis easier without losing too much generality. In fact, now we are interested in looking carefully at the textures of these interactions and looking, I mean, we are more interested in looking at the partial mixing with the different leptons, with the tau, with the muon, and with the electron, and this will play a role in that.
Can you go back maybe 1 or 2 slides, because you had, I just want to see your field content again.
Yes, so
yeah,
it's basically the scalar and this part here. Yes. So this is one of the main results that we will present. I mean, this is a partial results, and now we have to compare this with experimental bounds, but here you can see how powerful introducing these Yukawas can be to change the instability scale. So you can, using lighter neutrinos, and well, Yukawas of order, they have to be a little larger than 1, but this is still allowed for between 3 and 1, let's say 4. Anyway, this can change a lot the value of the instability, of the metastability bound, and render it as strong as 1 PV.
So sorry, just to clarify, you have 3 right-handed neutrinos and a singlet is what you're adding. Is that correct?
Yes.
Okay.
Yes. That's the model. Okay, so now
not a real singlet. That's also important.
It's actually a complex thing, yes. And we actually neglected the effect of, I mean, of the Majoron, which is actually, we were interested in the effect of this very heavy resonance, right? The modulus of the field, which will be the heavy degree of freedom, which stabilizes at large energies the
complex singlet, as you're saying.
Now we realize that there could be some interesting effects also coming from the other one, from the pseudo-Goldstone boson, and are looking also a bit at some of the different breaking patterns that one can use and how this would affect the calculation. Yes. Okay, so anyway, we see here how this can be very strong, but actually, like when we look at the bounds, we will see that some of these nicer regions are excluded, but there is still plenty of space, and there is regions where we could say that we could actually solve the Higgs hierarchy problem completely. So now I will just quickly mention that the exoscalar content of the theory, which is indeed a complex scalar singlet, makes for a more complicated potential, a two-field potential, which involves the Higgs and the new scalar field. As I say, we didn't consider yet, we just considered the other a massless pseudo-Boston boson. And especially relevant will be the coupling between the Higgs and the scalar, which we name kappa. And this potential can have a number of Víctor configuration, of which here we listed all of them. Actually, well, we performed a small analysis, a very simple one, but basically we realized that what controlled the vacuum configuration in this potential were just these two parameters here, and depleted all the different configurations that could happen. So there is this in total 9, oh my God, 9 phases, I'm sorry, 9 phases, and we found that there were some regions in terms of these parameters which were ruled out, and this gray region actually, well, by the definition of these parameters, they cannot be accessed under the assumption of unboundedness from below for the potential.
Sorry, Victor,
So,
you will come back to the pseudo-scalar rate later, right? Because I have a big bunch of questions regarding that.
Not really, because this is still unpublished work, but we can discuss
okay.
it.
Yeah,
Yes.
but now I see why Belen wanted me to come to Madrid, because she did ask me something about this, and I told her a long answer. Yeah. Okay. Yeah. Sorry. So carry on. I'll
Yeah.
ask
So
her.
I mean, if at the end we can discuss or whatever.
Yeah.
Like it's
Mhm.
yeah. Yes. Okay. So this is just very quickly. So this is these are all the possible vehicles which can appear in the theory, which can be rewritten in terms of the signs of the mass operators and these omegas. And that is also true for the derivatives and second derivatives. So you can actually perform the full classification in terms of these degrees of freedom, which is something very simple, but which we had not seen in the literature before. So we added it to the paper. And okay, so there is not all of these configurations are adequate to produce the right conditions for what we are doing. And we chose this phase 4, which is among the ones which are indeed which are adequate. And in this configuration, we considered this saddle point P2 to be the Electroweak minimum, while this will be the ultraviolet minimum to which it can tunnel. And at the classical level, this is a saddle point, but once one considers the one-loop Coleman-Weinberg, a small barrier develops here, which exactly mimics this potential that I showed earlier. And well, this is a 3D version of this, so you can see the Electroweak vacuum is here, and you can actually tunnel to this true vacuum from it. And okay, here I added this plot where you can see what would happen without the scalars. Of the heavy neutrinos just make the potential extremely unstable, and the scalar, what it makes is it creates this ultraviolet vacuum, which will soften the behavior of this tunneling. Okay, now I will go very quickly through this. We actually, I mean, one of the things that we looked at was precisely at the tunneling rate from the Electroweak vacuum in this configuration to the true one. And what we found, well, what we used is a simplified we realized that it was better, it was simpler to do the instanton, calculate the Euclidean actions and all these things in a one-dimensional potential, which which was defined for the combination of the fields, which goes in this direction and corresponds basically with the trajectory that a classical ball will follow to go from the top of some hill of this, right, to the bottom, to this minimum. And well, we performed the calculation of the Euclidean action. Of course, the potential that you obtain is the same with the opposite one, and the instanton configurations, which minimize that action, correspond to the ones which go through this reach. So this is okay. And now I can okay. The second part of this paper consisted on finding out whether we would be able to find to prove these scenarios in future colliders, and these are the bounds which we use for the neutrino space. So for lower energies, we used measurements of or limits on the missing energy at the set pole obtained by the Delphi collaboration, which are actually very old, but there seems not to be a big improvement coming from later experiments. And for larger energies, which actually will turn out to be more relevant, we used the limits which come from the searches. Well, from considering the violation of the unitarity of the PMNS matrix, which basically involves the non-observation of flavor-violating processes in the lepton sector, Electroweak precision observables, and this kind of thing. And we use the global fit in this paper. And an assumption that we took, as I said, this is something that we want to revert, is that well, since we are only sensitive to the trace for the calculation of the metastability bound, these bounds are only for the trace. And we assumed that the major contribution, the dominant contribution to this trace came from the mixing of the neutrinos, of the right-handed neutrinos with the tau neutrinos, which actually provides these are basically the weakest bounds. So this is a conservative assumption in what concerns the future colliders, because we will get worse prospects, but optimistic in what concerns the excluded regions, because we will get less constraining limits, experimental limits. And for the scalar space, we used some of the results in this paper, in which they performed an Smeft operator analysis of models involving the Higgs and some scalar singlet. Well, these are all the operators which are generated at one loop from integrating out the scalar, which we have taken to be heavy, and so we have integrated out. And well, maybe the only relevant thing to say is that the dominant effect comes from these three operators, and actually the only one which has a contribution, a non-vanishing Wilson coefficient at the level, is this one, the OH box, which will therefore be the most relevant one for the calculation. And in fact, the most important bound is the one at the FCCHH, which we calculate, well, we consider the contribution of this operator to the Higgs trilinear coupling, which, well, this is an operator which contains derivatives, so it messes up the canonical normalization of the Higgs field, and when you restore it, what you find is that this operator will enter the potential and will generate these kind of contributions from the trilinear coupling. So we used results by Mangano and collaborators, and in particular their prospect that we will be able to measure to constrain this ratio, like the ratio of the measured trilinear coupling of the Higgs and the prediction in the standard model to approximately a 3% sensitivity, well, a 3% accuracy. So this makes the purple bound here. And for the rest of the bounds, which are subdominant, what we did is we used this global fit by Celada and collaborators, taking into account all the operators, although, as I said, so this is, yes, this is the whole fit that they made. Actually, the LHC the LHC bounds are all taken to 1 here. So this is the ratio between the prospected one for future experiments for the high Lumi LHC and the FCC-EE. And here you can see the improvement prospected for the two experiments, right? And actually, the most dominant operator, the most relevant operator will be this one in our analysis. So, well, you can see that how, well, this improvement is the one that gets reflected here. Okay, and now this is the integrated plots with all that I have presented so far, the result plots. And what they tell us is that some of the most interesting parameter space is already ruled out, but there is some remaining that is actually under like in the sensitivity region of the FCC-EE. And we can highlight this region here where we get a stability and metastability bound of the order of 6 TeV, which is still low enough to account for the Higgs hierarchy problem. Here we have the same, I mean, of course, if we found something a little bit farther from there, it would also be interesting. As we go to regions in which the bound weakens, of course, the scenario will lose some of its nice perks, right? So if we don't detect this at the next generation of colliders, which will prove this region, we could say that, I mean, the point is that this is a scenario that will be proved that we will measure in the next generation of colliders. And if we do not, then, well, the motivation for it will be weaker, and we want to see this as an iceberg, right? Since we won't have to wait much until we actually check whether this scenario is realized or not in nature. And well, in the scalar space with kappa and the mass of the scalar, and also the quartic coupling of the extra scalar, we actually looked at different combinations which are in correspondence with these benchmark points here. And for instance, with this one, where the mass of the neutrino is about 5 TeVs and the Yukawa is 1.8, we find this result here, where the region in which the tunneling rate is from the Electroweak vacuum to the ultraviolet one is small enough, which is fully in the sensitivity region of the FCC-HH. And in this red region, the Electroweak vacuum is too unstable, and here the full potential becomes unbounded from below. So, well, this area is excluded. This is a story.
Can you tell me what the VIV of the singlet is?
The VIV of the singlet?
Yeah, what is the scale of the VIV of the singlet? Yeah, because I saw the singlet mass, but I don't, did I miss it? Did you show?
Yes. So you can read that out from the value of this scalar, right? So the VIV should be,
yeah.
Yes, it should be just the mass, the VIV squared is the mass squared over the lambda. So it should be, in this case, 1 order of magnitude above the other. Well, a square root of 1 order of magnitude, so a factor of something. Yes.
Got it. Yeah, thank you.
Okay. So this is an overview of all the scenarios which we considered, and you can see that it is pretty generic, that there is a nice overlap between the sensitivity region of the FCC-HH and these regions where the scenario is realized correctly with the right, with a small enough tunneling rate, and well, with a strong metastability bound. Okay, and now I will actually finish. I don't know. Yes, it's about time. I've been talking for about an hour, I think. So just let me brush over very quickly the other models which were in the literature. This is by Maximilian Detering and Tebon Yu. And they consider an action with this potential here, which couples to the Higgs, and found that the the metastability bound is modified like this. So basically this is the same as ours, and then they have this term. And also that they get this threshold correction to the potential, to the quatic of the Higgs. And their results look like this. So they find exactly the same behavior. So of course, the regions in which the metastability scale is lowered. So this is, the color is the ratio between the, yes, it's, sorry. Okay, anyway. Yes, it's a mass term over the, but basically, yes, the red regions get you a better metastability scale, which is closer to the measured value of the Higgs. And they see that the most interesting regions are close to the regions which have already been excluded. And well, most of the interesting regions will actually be ruled out, or maybe we find something there by the FCCEE, where the bounds they consider are basically from the search for invisible decays into the S, which is actually the axion, like they called it S in these papers. Yes, and okay, this is another example by our collaborator Thomas and Sim Benavides from MIT, in which they consider vector-like quarks, which couple through Son-Yukawa coupling to the Higgs, and they find, again, the same behavior, right? So you can see that, well, this is the interesting regions, for instance, when the metastability bound is smaller than 5 TeVs, are just at the sensitivity regions of future experiments and close to our current sensitivity. And, okay. So this is it. As a summary, I just want to, well, remind everyone that there is this metastability bound, which allows, when it is enhanced in the presence of new physics, to actually introduce a new class of viable solutions to the Higgs hierarchy problem. And that particularly in our model, well, this is actually focused on the people from the experimental workshop. We will have a better sensitivity for the right-handed neutrinos at the FCCEE, and in the case of the scalars, we will detect them if they were to exist in the FCCHH. And okay, here, this is the end of my talk, so maybe we can have some questions.
Thank you so much, Victor. Yeah, there was a lot to think about. Yeah, the floor is open for questions. I have a bunch, but I'm very happy to keep them for after the recording stops, because they're very detailed.
I'm just still trying to get my head around your model. Just you have a set of right-handed neutrinos, and you've introduced the complex singlet. But you broke the symmetry of so there's a U1 symmetry associated with that complex singlet, but you've broken that symmetry. So what happened to the Goldstone boson?
Yes, so that's also what we were. So the Majoron, which is this Goldstone boson, could play a role on some interesting phenomenology of the model. We actually neglected it in this case. So it's usually a lighter particle which will. Well, we argued when we made this paper that will play no significant role in this setup, right? So we only focused on these other two particles.
Yeah, but you could have gauged your model. Could have put in an extra U1 gauge field associated with that symmetry.
They could have, yeah. Yeah, but I guess, yeah, that would have given them a Z prime, and the Z prime stabilizes the Higgs potential in a similar way.
Yes. So actually, we will probably wrong in neglecting it, and some interesting stuff can come with it, which can actually improve what we presented here. Yes, this is what we actually didn't want to deal with the different breaking patterns to give it a mass to it and so on. So we saw it as a nice assumption to start by just considering the other one.
I think you probably don't have any choice because you've got a massless particle in the model that you're dealing with, and that's going to dominate everything.
Yes, well,
as they've written it, you could read it as if it is a real scalar. I don't think you would have would have messed things up. But also, if it is a complex scalar, and so they would have to introduce a mass term by hand. But so this is what Belen wanted to talk to me about in detail, is that what people don't, I guess it's surprising.
You're saying a mass term by hand but you're not going to get a vacuum expectation value for this one now. Is that what it is?
That's my point. You cannot, because CP is protected. There's no way you could break CP in a setup like this. So you would have to introduce the mass term by hand. There's no other way about it. And it would be, so it's going to be the only CP odd particle in there. So it will always come as a pair. So it wouldn't, then depending on its coupling to the Higgs, it will stabilize the potential even more. So it will contribute positively to the running of lambda. And it would be through that. So if you go back to your potential, I've forgotten, was it on slide 33 or further back?
43, you said.
33. Well, that's I've written here about the pseudo-scalar, but it might not be where you showed your potential first. Yeah, we're getting close.
It was 34, I think. Yes.
Yeah, here. So the mass term or the interaction term with the pseudo-scalar and the Higgs would be through kappa again.
Yes.
Yes, because that S squared has whatever let me call the CP even component sigma and the CP odd component eta. You would have sigma squared plus eta squared there. So yeah, it would be the same coupling.
Well, not actually. I'm not sure right now, right? Because if you so this is the same as I assume that these are the non-lepton or the yes, these are the non-lepton number breaking symmetries because right.
Yeah.
Because the Majoron is defined through the spontaneous breaking of lepton number, if I remember correctly. Now this could be, but actually, I guess that the contributions. So in the potential, the extra pseudo-Colston boson would only appear through terms which break its associated symmetry. And this is not kappa, right? This should be something else, so we are actually considering terms like S squared without the modulus plus the conjugate and things like that. And will give us the interactions.
Yeah, so at this point, your model has an explicit Z2 symmetry, right? So your pseudo-scalar, if you were to give it a mass, so let's assume that you will give it a mass because you will have to. Could be your dogmatic candidate or whatever. But if you were to introduce cubic and I guess linear terms, well, the two are going to be dependent. So you could rotate one of the terms away, but then you will have interaction terms specifically for the singlet with the Higgs. Whereas as of now,
it's real now, Venus, is it?
Sorry?
Assuming it's a real singlet.
Assuming it is a real singlet, yeah. Or let me see. So if they were to write cubic terms, it would be S plus S star times S star or S squared modulus. Yeah, so it can be complex as well. And you can introduce one of those cubic terms. Yeah, so in that case, the contributions, let me see. Yeah, you will have then extra couplings that would couple your singlet to the Higgs. But as you've written it now, there is a Z2 symmetry. And yeah, it's just the kappa. So I don't think you're missing out on much.
Well, now, because now I don't remember the exact symmetry. I mean, I know there is some U1 symmetry in the Majoron model, which prevents us from, so this is actually a U1, not the only set 2. Of course, they look the same.
Yeah.
And then you break that. Yes, you break that when you want to generate a mass for the other guy, right? And we in our paper we actually discretely write some generic breaking point, breaking symmetry breaking term, and just specify that this is required for the mass of the Majoron to appear, but not specify more. Yes, so, and I don't really. Yes, so there is, I guess Belén is actually right now a little bit, there is so many options, right? If you want to break the symmetry, that generate different stuff, that this is what we are looking at now, and trying to decide whether to consider, which combinations to consider, and whether all of them are relevant, and this kind of stuff.
Sorry, you're breaking up, but I don't know if it's because of my internet connection or yours. Well, Denjo also seems frozen, so I guess it is my internet connection that is unstable.
Sorry.
Yeah. Yeah, my internet connection, it says it's unstable, so I didn't hear what you said. Sorry. Could you repeat?
Well, sorry. So I just I was saying that indeed this potential doesn't break this symmetry, and that in the paper is really added a term saying that this is the term which contains all the different breaking contributions, symmetry breaking contributions, but we just didn't specify, and that this is the problem that we are facing now, that there is many different options which might have so you need to sort out which physical, I mean, we need to sort them out and see what are the physical consequences of all of them, and whether it is worth to consider all, or just this kind of stuff. Yes, so.
Yeah, but I mean, as you said, there is a U1 symmetry with a Z2 symmetry as a subgroup. So you could just add a soft breaking term and say, here it is. We have a CP odd component that is stable by itself, but it wouldn't contribute. So what I'm saying is that its contributions to stabilizing the Higgs potential is through that kappa term, the Poisson coupling. There is nothing on top of that. So yeah.
In this work, this is the only.
Yes. Yeah.
This is what I mean. This is the only coupling to the new physics scalar sector. So this is what will contribute the most to stabilizing it.
And then you said you considered. So right now, the analysis that you showed is in which the fermions are lighter than the extra boson, right?
Yes.
And you said that the reverse wasn't viable?
Yes, so the thing is that we actually looked at it. We didn't look at it thoroughly, but it seems that if you do the opposite first, if you want a strong enough bound, you will need that these are not much more than an order of magnitude apart. Typically, also what you find is that the stabilizing effect of this guy will make the instability bound appear even more apart, right? So typically, what you get in those cases is just a case in which you get a very improved bound, but it's still like 2 orders of magnitude or 3 orders of magnitude from the value of the actual value of the mass of the Higgs. So then it's not such an interesting scenario.
Yeah. No, that makes sense. Yeah. And I guess it justifies why you can see your scalar in FCC-HH, whereas the right-handed neutrinos you could see in FCC. Yeah.
Yes. Like, I mean, you need to go to higher. Like these guys are really heavy. The scalars in this particular setup. So.
Okay, so then you had sorry, anybody else before I jump in? No, okay, then I'm gonna keep on asking. So if you go a little bit further to where you had on your plots you had a sine of theta, but I think it might have been from the Alp paper with Tevong and was it Jian?
From either of them?
Yes.
Yes,
Yeah.
here.
Yeah, so here you have sin theta. This theta would be the mixing of the CP even component with the Higgs, right?
Yes, I might not. I thought that I should have put it here, but I guess it should look something similar to this. So I mean, yes, it's a mixing between.
Okay.
Mhm.
Yeah. So and then go back to that plot. Okay. So MA. Oh, so this A is this the pseudoscalar component, right?
Yes.
So the fact that you could yeah, so naturally I would assume that these two things are completely independent from each other, right? Sin theta depends, or the allowed values of sin theta depend on the mass of the second scalar, the CP even scalar, but not on the mass of the CP odd scalar. So I am a bit confused how to read this plot or what to understand from it, because so what is the mass of the CP even scalar in these plots? Do you know?
Not really, but I mean, which I'm not sure if I am.
Yeah, let me look here.
I say that there is only one pseudoscalar degree of freedom, in physics degree of
Okay,
freedom.
so I see.
Yeah.
Okay, so it's not the
Yes.
usual. Yeah, it's not a
So of course,
pseudoscalar.
yes, of course there should be. I mean, I don't know if you are referring to the resonance that usually you have for the axion models, right? So you get some very heavy resonance, which usually people doesn't care about, and I think that this is the case. So they only consider the effective coupling to the Higgs through these couplings here, and the Higgs well, of the axion to the Higgs, and there is only. I mean, the new physics scales are the mass of the action and the typical scale of the action, which would actually be the dev of one of such very heavy scalars if it was one of these realizations. So maybe, of course, maybe you were really, you were referring to that. So.
A bit, yeah, I see. So you have the mass of the Alp there with the F, which is the dev of it. I see. Okay.
Yes.
Okay. Yeah. So
Yes.
they are connected. They're not completely independent from each other. And the
So
point
in the case,
is that, sorry, go ahead.
No, only that is like in the case of an alp, they should be independent from each other, and you cannot impose any relation. At least if you work as generically as they did. Let me see, because okay, I mean, so it should be, maybe you can replace. I don't remember. I guess that I don't see how the calculation should be different. So probably it should be like a larger scale will get you a smaller sign. And this is how you should read it. Like this is goes with the inverse, this sign of the. I don't. I mean, yes. So I don't know. Like once you see that, I don't know.
It does make sense because so one usually sees these plots with the LHC bound, which is so high up compared to what is L3, the cyan one? Is that L3? It's there is a cyan thing. I might see. Is it L3 or 1.3? I don't. Yeah.
Which one? So there is a LEP and there is Hilumi, FCCEE, and in GigaC.
Yeah, but there's a blue cyan one. Yeah, that a little bit down.
Yes. This one.
No, a bit higher up. It's a colored region. Yeah, that one. What is
No,
that?
yeah,
Yeah.
that's L3. I didn't even realize that was there.
Mm.
Yes, so
So what
yes,
is it?
it's
What is
like,
L3?
I mean, at the moment I don't know. I can check because as I say, I just didn't see the color is so faint. I don't see it. But it could be. I mean, everything else here are colliders, so it would be. I wouldn't expect it to be something else. So I don't know if this is, but this is an experiment that has been already.
No, I get that. Yeah, just I didn't know what it was.
No,
But,
no, no. What I mean is that this is not a future experiment, but an experiment that has already produced data. So I am really.
Okay. This is from the
Yeah,
paper of Tevang and Maximilian, right?
yes, yes. I mean, I could even check now there.
Yeah.
But yes, I mean, by the color, yeah, I assume that this is something that already has produced outcome. So not a prospect, but I don't really know what.
Yeah. Oh, I see it. Okay. It's a detailed image that it struggles to go through.
Mhm.
I don't see what that is.
I mean, I don't know if it could be like an action experiment or something, because it indeed has a very good, it goes much beyond what LHC is capable of. So it could be some dedicated experiment that.
And why
I
is
am right.
so the high Lumi LHC bound on this mixing? There's a spike around, what is that, mass 20, no, was it 15 or so GeV, 14 GeV?
Yes.
Why is that?
I mean, also, I don't know if I can answer that, since this is, I don't think it's something they comment on in the paper. So I cannot say much more about this analysis.
Yeah, must be a resonance of something.
Yes, indeed.
Yeah, that you can't
But
rule out because that specific process takes over. Okay, good. Then you had on your slide 43. This is not a physics question. It's just
yes.
it's a issue that I'm dealing with these days. It's kind of finding the direction of steepest descent in a potential that has many variables. I wanted to see, so this plot on the right, what program did you use to produce this? Is it a
So this is actually, yes, so for this tunneling calculation, we had our own dedicated program. Yes, and it actually, in our case, we didn't have that many variables, but the problem was that these, for the combinations of parameters that we needed, this region is extremely flat. So no integration, like for some of the calculations, for instance, to find this trajectory.
Yeah.
So it should be very easy with any, like with NDSolve or something like that, right? But NDSolve was not able to advance.
I know, yeah.
Probably that's the problem you had. So this is something, I mean, I know the artist was Thomas Steingasser, our collaborator. I asked him, but he devised a way of integrating this. Actually, he just did it pretty much by hand and using a very, very large numerical precision in this particular,
What's the name, did you say?
He's Thomas. So the other paper, Steingasser.
Oh, okay, yeah. Thomas at MIT, yeah, I see, yeah. Because I know another Thomas who does these calculations. Okay. And that code is not public, is it?
No.
No, okay.
We have not. I mean, we could. I mean, we could say, show it to you or something. I mean, I could talk with him. For now, it's basically, it's very, it's this kind of code that some work would be needed to publish it, let's say. Yes.
I know, yeah, because usually people use phase tracer or Cosmo transitions even, which is I have to be very careful what I say because this is recorded. It's not the most up-to-date code on the market.
Yes, like it indeed, like we actually tried to use that at first, and it indeed has like limitations. If you consider like very canonical scenarios, they work very well. But if you want to tweak your variables in some other way, it's problematic.
Yeah, absolutely. Yeah, so I've asked my questions. I just have one last one, which is a very difficult question. So don't feel bad at all if you can't answer it. So on slide 50. Slide 50. Yeah.
Slide 50, yes.
Yeah. Okay, yeah. So at the bottom, you have these corrections to the trilinear coupling, right?
Yes.
So during the conference last week, Ben Stefanak gave a talk, and afterwards he pointed this out to several speakers, but I was talking to him afterwards about it, and he was worried that people haven't really understood what he meant. So what he said was that when you are looking at higher order corrections to the Higgs triple Higgs coupling, if you have already taken into account the corrections to the Higgs mass, then you don't need to worry about the corrections to the triple Higgs coupling, because whatever contribution to Higgs triple coupling is you're going to have will show up in the Higgs mass, right? Because that's exactly give one of the Higgs a wave, and that would be your Higgs mass correction. Is that something you have thought about?
Yes, I mean, I don't know if so we consider very careful all this interplay between the different contributions to all the this is in one of the appendices of the paper. Basically, yes, so you need to define some observable scheme, right? Okay, so there is several moving parts for this actually, but indeed, normally one considers, we consider a scheme which I believe in the end it was the MZ scheme, where we consider measured values for the mass of the Higgs, that of the Z, that of lambda, and that of the charge of the electron, which is irrelevant in our case. And then we redefine all the variables, so accordingly to that. So in the end, many of the corrections, for instance, in the mass of the Higgs, get absorbed into the trilinear and the quadrilinear couplings and all the other couplings. I don't think they, because I don't know if I understand fully what he said, because I don't see how, I mean, I don't think that all the contributions cancel. So in the end, when do you do this and you get your clean mass of the Higgs redefined with no corrections, and then you get the corrections in all the other places, you still get these corrections. So I am not sure.
Yeah.
I mean, we probably agree, but I would like to see his calculation more in detail. I cannot recall it now in detail.
Yeah. Yeah, I mean, that is the extent of my knowledge that, but as you say, it could be that for specific scenarios, it is that one of them covers all the contributions from the other. But yeah, that might not be the case everywhere. Yeah, anyway, thank you. Yeah.
So, yes. So because also like, I don't know if I added No, I don't think I added a backup with this, but yes, you can see how there is partial cancellations between the different corrections, so that in the end you get a different coefficient than you get at the beginning, and there is this sort of thing. But to my knowledge, there is not this total cancellation in the generic case.
Mhm. Good, good. Thank you. Anybody else? If not, I will ask one last question. So in the very first slides, you had that famous plot of the SM vacuum sitting in that little thin space of metastability.
Yes, the Butazzo
Yeah,
and
that one.
collaborators. Oh no, it's too much. Yes. Here.
Well, yeah, so this one, I think they're from the same paper, and the next one that has the
Yes.
you know which one I mean?
This one.
Yeah, that one. Yes, it is from the same paper. Yeah. So this is from 2013, and as far as I can remember, whenever I've given a talk or seen people give a talk about stability, it's always been these plots from this paper. Do you know if there's any improvement on this, or if somebody's redone the calculations with better precision? Do we have better precisions on top mass alpha S, or this is it?
I mean, I know I can point in the Detering and You paper, they actually did, I believe, these plots, and I couldn't sense any
Difference.
difference between them. So there might have been some improvement, but it has not changed too much. Now, at least that I realized, because of course things could have moved, right, slightly and so on. I know that for the other this other plot that I showed is actually a little bit outdated, and you can find some of those which have slightly better, not extremely better, but slightly better limits. But
is that in the references of your paper? Can I look that up, or do I have to go digging?
Sorry again. So what?
So the reference that you said has improved on the previous plot a little bit.
So I mean, it's the Detering and You paper, so you have it in it's the one I referred to at the end, the one with the axion-like particle, I mean.
Okay, got it. Yeah.
So I mean, just so that you see the number.
Oh, the authors, yeah.
Yes. Yeah, so it would be this number here.
Yeah. Okay, fantastic. Thank you. Okay, well, I'm out of questions. So maybe we could thank Victor again and stop the recording.
Thank you.